Welcome, welcome. So we are now in our section 5 note packet, starting to look at functions of random variables. And so we're going to, or depending on when you're watching this video, we might have already done the second page on linear combinations. And so we won't spend a lot of time here, but one thing to quickly note is that this page only gives us the expectation of u and the variance of u, where u is this linear combination of a bunch of y random variables. It does not give us what the actual distribution of u is. And so that's what we're going to start thinking about on this next page. So I'm now on page 3, looking at the method of moment generating functions to actually figure out the distribution of u, at least for a very particular case, is what we're going to start off with. And so to get us going here, let me pull out my highlighter. The setting that we're in is we're supposing that we have this random variable x, and we know the distribution of x. So x is normally distributed, x is exponentially distributed, x is binomially, or it follows a binomial distribution. So we know the distribution of x, but we want to know the distribution of u, which is some function of x. What we could do is compute the moment generating function of u, and then see if we could identify that moment generating function as an MGF for a known random variable. This part is very, very general. And so what we're going to focus on in this video is a very specific case. So we're going to focus on this setting where if we have a bunch of random variables, y1, y2, yn, and we're interested in the distribution of the sum of those random variables, then we have this theorem that we can figure out the moment generating function of u by multiplying the moment generating functions of y1, y2, yn all together, and then hopefully that is a common moment generating function that we can identify with one of our sheets. A couple of keys here. First, we do need this assumption that the y's are independent, so that's a necessary condition for the theorem. And then second, the sum itself might not seem super useful, but it's not too much of an extension, and I'm going to erase this so there's no need to copy this part down. But it's not too much of an extension to extend that over to the mean. And so eventually this type of problem will have some use because the mean is a very useful quantity in statistics. But for now we're not doing that, so I'm erasing that. We also have this corollary that if y1, y2, yn are both independent and identically distributed, in stats, we write this down often as IID. Then we could just take the moment generating function for one of those variables and raise it to the power n. And so I've chosen y1 here, but that doesn't matter. It could be y2, it could be yn. It doesn't matter because they're all identically distributed for this particular corollary. Okay, so let's jump into this example then. So we have x, which is binomial with n1 p, y is binomial with n2p. We have this third important condition that x and y have to be independent, and we could then apply the theorem to find the distribution of u, which is x plus y. So let's do that. I'm not going to jump to the cheat sheet, but if you have your cheat sheet handy, you could look at the moment generating functions for a binomial random variable, and that gives us this. And then because p is the same for x and y, that allows this nice simplification where the moment generating function of u is equal to that quantity raised to the n1 plus n2 power. So what distribution does this moment generating function correspond to? Well, actually the same as what x and y were. So this is a binomial with n1 plus n2 as the first parameter and p as the second parameter. When you think about this, this does make sense. I think when we introduced the binomial, we used an example of shooting free throws. So you might imagine that, if I shot 20 free throws and then I immediately shot another 15 free throws and my free throws are all independent, then the distribution of adding the number of free throws that I've made out of those 20 attempts to the number of free throws I've made out of those 15 attempts would just be the same as a binomial 35p random variable. So that's kind of the intuition with what we've done here. Note that p, for it to be this known distribution, p does have to be the same in the two variables. So if Steph Curry shot 20 free throws and I shot 20 free throws, and then we added those two random variables together, where the random variable is the number of free throws we each made, we could still use this to find the moment generating function, but it will no longer follow this binomial distribution, which should again make some intuitive sense because now the p's are quite different. One more quick example. So now we're supposing that we have IID random variables that follow an exponential lambda. And so we're going to make use of that little corollary where mu of t is going to be just one of those moment generating functions raised to the n power. And again, you could verify on your cheat sheet that the moment generating function for an exponential random variable is lambda divided by lambda minus t, implying that the moment generating function of u is lambda over lambda minus t raised to the n. And then again, it's kind of this matching game where you're looking for a random variable that has this moment generating function. And this, you could see on the sheet, is a gamma random variable with n and lambda as the parameters. Okay, so your prep quiz will have you practice a little bit more with this, and then we will also do a couple more examples in class as well for a little bit of extra practice.